Continuing on with the logical group of instructions of 8085, we have studied 9 so far. We need to study 10 more. There are 19 instructions in total, and the first 9 are covered. So instruction number 10 is CMPR. So what the instruction does, it basically compares the contents of the accumulator with the contents of a register, and the result will be inferred by the status of flag. So you can see if A is greater than R, then carry and 0 will be 0. If A is equal to R, carry will be 0, Z will be 1. If A is less than R, carry will be 1, Z will be 0. There will be no effect on the contents of the accumulator and the register. The flag status will basically help us in inferring the result, whether A is greater than R, or whether A is equal to R, or A is less than R. So this is the compared CMP equation of CMP instruction of the microprocessor. So rest of the properties is a single byte instruction, has only one machine cycle, has 40 states, execution time of 1.2 microseconds. The variations, depending on the number of registers, you have 7 different variations, and all the flags will be affected depending upon the status of the result. As we have already discussed, the carry and the 0 will infer the results. Addressing mode is the register addressing mode, and the destination is implied in this case. The micro RTL only consists of the opcode fetch machine cycle, and opcode fetch machine cycle, as usual, you have the 40 states, and in the T4 state, CMPR will be equal to 1. Next instruction we have is CMPM. Just like CMPR, this is used for comparing the contents of the accumulator with the contents of the memory location of the addresses specified by the HL register pair, and the result again will be inferred by the status of different flags. As you can see, the flag status will still remain the same whether A is greater than MHL, A is equal to MHL, A is less than MHL. Accordingly, you can decide which you can compare the two operands. Again, it's a single byte instruction, has 2 machine cycles because if I have to read from a memory, so it has also a memory read machine cycle. Therefore, the number of T states will be 7. The execution time will be 2.24 microseconds. The variations in this case, it's only as itself exists as itself, equals CMPM. All the flags will be affected by this instruction, and they also help us in inferring the results. The addressing mode, source is register indirect addressing mode, and for the destination it is implied. This is the now the micro RTL of this instruction. You have the opcode fetch machine cycle, and you have the memory read machine cycle. Opcode fetch machine cycle, as usual, in the T4 state, CMPM will be equal to 1. And you have then the memory read machine cycle. You are loading the address bus with the HL register pair. So moving on to instruction number 12, we have CPI data. So it is used to compare the contents of the accumulator immediately with the data byte provided with the instruction itself, and again the flags will be used for inferring the status of the result, whether A is greater than data, equal to data, or less than the data. Rest of the properties, it's a 2-byte instruction because the data byte is being used here. It has 2 machine cycles because the data has to be read as well. So there's opcode fetch machine cycle and the memory read machine cycle. Accordingly, 70 states and an execution time of 2.24 microseconds. There will be no variations. It exists as itself only. This is an example of this system, and all the flags in the compare instruction, all the 3 compare equations, instructions that we have studied, the flags are affected. Source here is immediate, and the destination is implied. The micro RTL of this instruction. Again, you have opcode fetch machine cycle and the memory read machine cycle. As usual, there is no change. In case of immediate addressing mode, what memory read machine cycle, we have the program counter loading the address bus. Next, four instructions are regarding rotate. So first of them is RLC. So what it does is it rotates the contents of the accumulator towards the left. That means AI will become equal to AI plus 1. In other words, we can say the most significant bit will become least significant bit. The least significant bit will become the second most least significant bit. Second most least significant bit will become third most least significant bit, and so on. Also, carry will be loaded as per the MSB. You can see the example here, and you can see after applying the RLC instruction that all the bits of this, all the digits are rotated by left by 1 degree, and the carry carries the most significant bit. So it's a single byte instruction. It has only one machine cycle, that is opcode fetch machine cycle, and the number of T states here are equal to 4. The execution time is equal to 1.28 microseconds. It exists as itself only, as there is no, it is, and in this, using this instruction, only the carry flag will be affected. All other flags will remain unaffected for both head source and the destination. The addressing mode is implied. Micro RTL, it consists of only the opcode fetch machine cycle. Next instruction that we have is RRC. Now this rotates the contents of accumulator towards the right. That means AI will become equal to AI minus 1. That means the most significant bit will become equal to second most significant bit. The second most significant bit will become equal to third most significant bit. Also, the most significant bit will take its value from the carry flag, as you can see in the example. Initially, A is loaded by 110, 111, 01. Shift all the digits towards the right. You will get the output will become 011, 01110. And the most significant bit basically will take whatever the value of carry flag is. If the carry flag is right now 0, so the most significant bit becomes 0. If the carry flag were to be 1, then the most significant bit has become 1. Other properties of this instruction will remain same as that of RLC. Single byte instruction, one machine cycle, OT states 1.28 microseconds, and does not have any variation. Only the carry flag is affected using this instruction, and it's actually the carry flag plays an important role in the rotate instruction. Addressing mode is implied. Next instruction, so this is the micro RTL first. Same opcode fetch machine cycle, no difference here. Next instruction that we have is RAL. Don't confuse it with RLC. This rotates the contents of the accumulator left, but through the carry. That means AI will become equal to AI plus 1. AI plus MSB will become equal to carry, and carry will be transferred to the least significant bit. So what this implies is that the most significant bit will be transferred to the carry, and the carry will be transferred to the least significant bit. In the previous case, the most significant bit was directly transferred to the least significant bit. So here, the rotation will take place through carry. That's why it's known as through carry. Rest of the properties will remain same as that of RLC. RLC is not through carry. RAL is through carry. The wording The instruction sometimes confuses, but RLC is rotate contents of accumulator to the left, but RL is rotate contents of accumulator to the left through carry. The properties are same, and it will have only one machine cycle, that is the opcode fetch machine cycle. Similar to RAL, we'll be having RAR. So it rotates the contents of accumulator to the right through the carry. So this is the macro RTL of this instruction. The least significant bit will be transferred to the carry, and the carry will then be transferred to the most significant bit. The properties, they are same. Single byte instruction, one machine cycle, 4T states, execution time of 1.2 microseconds. Number of variations is it exists only as itself, and the examples are here. Only the carry flag will be effective using this instruction. The addressing mode is inside. So these are four rotate instructions: R, LC, RRC, RAL, and RAR. Next three instructions we have now. One we have CMA, simply used to complement the contents of accumulator. If accumulator has something, say for example 1 0, it will become equal to 0 1. Obviously it will be an 8-bit number. It will have 8 digits. So accordingly, each of the digit will be complemented. So it's again a single byte instruction. Then instruction itself only. We need to decode the instruction only. So we have only the code fetch machine cycle. The total number of states will be 4. The execution time will be 1.2 microseconds, and the number of variations of this instruction, it exists only as itself. We have an example in CMA. So this instruction basically will not affect any flag. And the addressing mode for the source and the destination both, it's implied. And the micro RTL, it consists of only the opcode fetch machine cycle. This was CMA. Now we have STC. STC is used to set the carry flag. That means carry flag will be made equal to 1. So we can use this instruction sometimes for different types of programming purposes that we'll be studying later on. The properties, similar to other instructions in this logical group set, we are saying. So most of these instructions that we are studying today, they have almost the same properties. They are almost all single byte instructions, apart from the one CMPM that we studied. And so this definitely sets the carry flag. So the carry flag is only affected in this using this instruction. For the source and the destination, the addressing mode is again implied. So we have only the opcode fetch machine cycle in this case. The last instruction now in this logical group set, we have instruction number 19. CMC, it simply complements the carry flag. So if carry flag was carrying value of carry flag was 1, it will make it equal to 0, or if the value of carry flag was 0, it will make it equal to 1. So other properties of the system will remain same, and as far as the flag status goes, it complements the carry flag, so only the carry flag is affected. Is the micro RTL only the opcode fetch machine cycle? Exactly no. So with this, we have completed 3 groups of instructions: the data transfer group, the arithmetic group, and the logical group of instructions. And they consist of the bulk of the instructions of the microprocessor. As we know, in the arithmetic group, we have 15 instructions. In the data transfer group, we have 15 instructions. Arithmetic group has 20 instructions, and the logical group has 19 instructions. For the rest, branching group has 8, stack group has 6, machine control group has 6. They are also very important, but since we have completed the bulk of these instructions, so before proceeding further, we'll be also starting now with some programming so that we get basically a feel about how these instructions can be used and how these instructions are actually occupying the space in the memory. We'll be able to understand what exactly single byte instruction means, 2 byte instruction. That becomes more clear to us. And we also learn something about the assembly language program. So we'll do some examples in the next session. After that, we'll be starting with the branching group and the stack group instructions. So hopefully you will go through the micro RTL of actually through the instruction format of all these instructions that we've studied so far. Uh, Clear your doubts about the micro RTL if there are any, and we'll proceed with the programming in the next session.